Yes. So all you would do, oh shoot. All you would do is once you've drawn your, all right, I just need to get rid of the whole thing. You just draw a little squiggle in it. So you have your y-axis here, right? And so you decide where is a good value for you to start with. And on the graph, it looks like, that first maximum point was like it was at -49, right? So there isn't any point to start anywhere before that. So here, right, wherever you're gonna cut out your portion, you just do, just a squiggle, okay? And then you say, okay, what number shall I start with? And you know what? Maybe this time around, I'm gonna start with -45. -45, -50, -55, -60, and so on. Okay? All right, that's a very common thing to do. And also, it's good practice for you guys to get in the habit of doing things like this, right? It just makes us like better mathematicians, right? Gavi?
Kind of just a random question about this. If we were to write or make a squiggly line on any of the other three places available, would it have to be the same amount from 0 as the other ones were?
Mm, no, no, it wouldn't. But you also wouldn't like you wouldn't cut out a portion here and a portion there either. You know what I mean? We normally just do it in like one location, one or like one place on each axis, you know? Tall?
I don't know if this is just my error or like it's a setting in the calculator, but I didn't get 0.29, I just got 0, and they both said that the y value was -49.
It might be because you don't have enough decimal places. So you're at the maximum?
I mean, no, I mean, when I get the maximum, it says 0.29,
Uh-huh.
which is right, but then when I just say trace graph and say x is 0, it still says y is 49. It doesn't give a decimal. So like, we know that the 0.29 is right, so that's what I should use for like increasing and decreasing.
So when I put in 0, I get -52. Is that not what you get?
No, it's not. I could check again. I mean, this was yesterday.
Okay. Okay. Any other questions? Ella?
I have a question on 44.
Mm-hmm. So, okay. So let's see.
Yeah, I'm still getting
You
-49.
are?
Yeah.
Okay. And you have your equation put in correctly, right?
Did you do cube root?
Yeah.
Hmm.
I was also getting that if that helps.
Yours is also doing that?
Mhm.
Okay, I'll revisit that then. Let me do this. So we have 4 equals -6 minus 2x. Okay, so remember what we had said yesterday is if you have 2, put 1 root on each side of the equation. So I'm going to move this one over here and make it 4 minus the root. Oops, equals. And now I'm going to square both sides. So here, when you square the first term, you get 16. The inside term is -8 times the root plus this the square of the root equals 31 minus 3x. So now I want to move everything to the other side, but first, let's see, this is -8 times -6 minus 2x. 16 minus 6 is 10 minus 2x. Okay? So when I move these over, I subtract 10 and I get 21. I add 2x and I get x. Right? So far, so good. All right, so now we're going to square both sides again, right? And what do we get when we square both sides? So what do we get on this side? It's going to give me a 64 times the stuff inside the root. And what's 121 squared? 144? What's 21 squared?
441.
41.
444. 441. Minus 42x plus x squared. Right? And when I distribute, I get -384 minus 128x equals this. So now I need to bring everything to the other side, right? And set this equal to 0. So I have x squared. I add 128 to the -42, and that's 86x. And I'm going to add 384. So what do we get when we factor here?
X plus
Okay.
11, X plus
Huh?
X plus 11, X plus 75.
Nice. Okay, so how did you do that?
It was a lot of guessing on my
Okay.
part, but I just found two numbers that added up to 86 and multiplied to be 825.
Okay, so that's amazing actually that you zeroed in on those numbers. And if you get stuck on something this large, right, you can like plug in this function into the calculator and see where it hits 0, right? And it'll be at -11 and -75. You could also use your calculator to do that. So x is -11 and -75, right? And so now what you have to do is you have to plug both of those numbers into this original equation. And when you do that, you actually see that neither of them work, right? So this one has no solution. Okay? Yeah, Ben?
Could we by any chance go over 82D?
Um,
I'm just kind of confused on what to write there at the end.
Wait, isn't it just A, B, and C?
82?
82 as D.
Just a sec. Whoops. Yeah. Okay. So the question there is y equals 2 to the x. And we're basically looking at, what happens if x is negative, if it's between 0 and 1, if x is positive. And now it says for theoretic conjecture about the relationship between the value of the base and the value of the power, if the exponent is greater than or less than 1, right? So if the exponent is greater than 1, right? So you want a conjecture that has the relationship between the base, which is 2, and the power, which is the value 2 to the x, right? So if x is greater than 1, is 2 to the x, right? What is that going to look like if it's greater than 1? It's going to be greater than 2, right? But then if it's less than 1, what's going to happen to the power? Then it's going to dip below 2, right? So that's the sort of thing that you want to say, right? You have 2 to the x. As long as x is greater than 1, then you have 2 to the 2, 2 to the 3, 2 to the 4. Your powers are going to be greater than 2. But once it's below, right, like 2 to the half, 2 to the 0, then your powers, your values are going to be less than the base, less than 2. Okay? All right, so let's go ahead and move on to our notes to the next lesson. And again, I'm going to do half of this today and half of it next time. All right. Okay. Everyone ready? Okay. So in this section, we're going to talk about polynomial functions. And okay, so let's define one more time officially what a polynomial function is. A polynomial function looks something like this.
We don't see the notes, Miss Amy.
Oh. Okay, so a polynomial function looks something like this, right? Where what you have is you have x's raised to the power of integers, right? So you have ax to the n, x to the n minus 1, and so on. The exponents are integers, and they can go from 0 to any number you like, all right? The leading coefficient is an, and that's the coefficient of the variable with the greatest exponent. So for example, an example of a polynomial function could be, 7x to the 5 plus 4x to the 4 minus 50x cubed plus 3x squared minus 2x plus 7. Okay, that's a polynomial function. All right, the standard way of writing it is in the order of decreasing exponents, and you see how the exponents are all integers greater than 0, greater than or equal to 0. And then since this has the highest exponent, that coefficient is the leading coefficient. All right.
Does that say 7x to the 9th?
It's a 5.
Oh.
And because that 5 is actually the highest exponent here, that 5 is the degree. of this polynomial function. It's the highest exponent. Okay. It's cool, Ezra. You're good. I'm recording it anyway, and so you're good. Okay, so let's talk about the first few degrees, right? The first one up is a constant function. What a constant function is, it's this. It's got a degree of 0, meaning it's something like this. F of x is equal to, let's say, 3x to the 0, okay? The exponent is 0, which means the degree is 0. And what's anything to the 0? It's 1. So this simplifies to f of x equals 3, and it becomes a constant function. So that has a degree of 0. Next, we have a degree of 1. So for example, f of x is 3x plus 2, right? The exponent is a 1. The highest exponent is a 1. And there is a little exponent of a 0 there, which we don't need to write. Next, we have quadratics with a degree of 2, right? Right? A random function. So that's how we can figure out degrees. It's just the highest exponent. Okay. What do graphs of polynomial functions look like? Graphs of polynomial functions are nice and smooth curves. Okay, if a polynomial function was a roller coaster and you were riding on the roller coaster, you would have a nice smooth curve, right? Basically, if you put your hand on it, first of all, you could just follow the whole graph without lifting your finger or your pencil. So that's a good example of a polynomial function, right? What is not a polynomial function? If there are any discontinuities, not a polynomial function. If there are any corners, not a polynomial function. Okay? No holes, no asymptotes, no corners, Okay, no vertical portions. Okay. So what we learned in the last lesson was that graphs of even degree monomial functions look like x squared, right? Like this. Graphs of odd degree monomial functions look like x cubed. Having that in mind, let's practice graphing one more time. If you have a function like this, 4x to the 6, remember when x is 0, y is 0? When x is 1, y is 4. And when x is negative 1, y is 4 again. So it's a very narrow function here. When I'm graphing these, you see how I first do this little cup at the bottom, the curve at the bottom, right? And then I do the edges. Make sure that when you're graphing these, you don't have a sharp edge at the vertex. Okay, then it won't be a polynomial function. So this one shifts to the right 4 and up 1. And it looks like a cubic, right? Like x cubed. So what I'm going to do, the middle point is here, right? At x equals 4. I'm just going to plug in the number right next to it, 5, right? So then I get 5 minus 4 cubed plus 1. That's 1 plus 1 is 2. And remember the symmetry here, right? So to the left, it's going to go 1 down. If to the right, it went 1 up. Okay. And if we wanted to put some more points here, I can also put in x equals 6. and I get 6 minus 4, 2 cubed plus 1, that's a 9. Right? So I can make it symmetric that way. How many points did we go up here? 7. I'm going to go down 7 and make it symmetric. Okay? All right. So let's talk about end behavior. When we graphed the monomials last time, right, it was just monomials. We said that for an even exponent like this, right, we said that both ends, right, the end behavior was either both up or both down, remember? And we said if we had an odd exponent, that one end would be up and one end would be down, right? Depending on whether its coefficient is positive or negative. So that was easy enough, you know, especially when we had the monomials. Now when things get super complicated, it turns out we can still use a monomial to figure out the end behavior, right? And here's how that works. So suppose you've got a complicated looking function like this. Look, this is not anywhere near the simple quadratic looking function, nor is this anywhere near the simple cubic looking function, right? But we can still figure out end behavior in the same way, right? End behavior meaning where does it go in the ends? To do that, what we have is called the leading term test. Leading term means the term with the highest exponent. Okay? So what you do is you take the term with the highest exponent and then you see if that exponent is odd with a positive, it's going to look like this. It's going to look like the cubic, up on the left, up on the right, down on the left. If it's odd with a negative, it's going to look like a cubic, okay? But with the negative option. If n is even with a positive coefficient, it's going to behave like one of these, right? You see how it behaves in the same way, both up? If n is even with a negative, it's going to behave like one of these. You see how both ends go down just like this one? Okay? Okay, so half of you, maybe all of you right now are probably thinking, okay, Ms. Malikian, it sounds like you make sense to yourself in your head, but you're not making any sense to me. Fine, let's do an example, okay? Look at this. Anybody have any idea what that function A looks like with that graphing? Do you, like, can you graph it? Like, can you figure it out precisely? No. But we can have a general idea of what the end behavior is, right? So we're going to talk about the end behavior here. Here's what we're going to do. Scan it for the term with the highest exponent. That's that one. That's the leading term. So now we just focus on this. Okay? And now ask yourself, 3x to the 4, do you know how that looks exactly? Yes, you do, right? What does 3x to the 4 look like? Does it look like that? Yes, right? So now can we figure out the end behavior of that quadratic looking function? We can. We want the limit of f of x as x approaches negative infinity. We want the limit of f of x as x approaches positive infinity. As x approaches negative infinity, where does the graph go? To positive infinity. And as x approaches positive infinity, where does the graph go? To positive infinity. So guess what? That means this function has this end behavior. All right? Any questions? Why does this happen? Why? Because look, where is infinity exactly? It's all the way here. It's when x is 1,000,000, 1,000,000,000, 1,000,000,000,000, even more. Let's take a small version of infinity. Let's say x is just a measly little million, right? And now imagine you plug it in here. X is 1,000,000. 1,000,000 to the 4. 1,000,000 to the 4. How many zeros does 1,000,000 have? 6. 1,000,000 to the 4 has 24 zeros. Compare that to 1,000,000 cubed. Only 18 zeros, right? It pales in comparison. Because of that, because infinity to the 4 is so much bigger than any of the rest, at the infinities, you can pretty much ignore all of the other terms. They become what we call negligible, which means can be ignored, right? That's why only for end behavior, we can ignore the rest of the functions, the rest of the terms. All right? Okay, so let's take a look at this next one. We're just going to take this, so it's going to be y equals negative 2x cubed.
Miss Malikian, wouldn't it be the negative 2x to the 5? Because it's...
Say that again?
It would be the negative 2x to the 5th because it's...
Oh my God, I'm so sorry. Yes. I fell into my own trap. Sorry. Negative 2x to the 5th, right? So scan it carefully. Thank you. So now what does negative 2x to the 5th look like? It's like an x cubed, but with a negative. So it looks like this, going down to the right. All right. So now if I want the end behavior, okay, as x approaches negative infinity, this goes to positive infinity. And on the opposite side, it goes to negative infinity. Okay? Questions?
Can you go to the page before really fast?
Mm-hmm.
Thank you.
Mm-hmm.
Thank you.
You're welcome. Okay, so from last year, do you guys remember, or I think we did it this year too, x-intercepts, right? How do we find x-intercepts? X-intercepts are where the graph crosses the x-axis, so we set f of x equals to 0 and solve. Other synonyms for x-intercepts are zeros, roots, or solutions. These are all the points where the graph crosses the x-axis. All of these are the x-intercepts. Now, that was not new. This is new. Turning points, guess what? They're points where the graph turns, right? Mind-blowing. These are points where the graph changes from decreasing to increasing and vice versa. So you see here, this is a turning point, this is a turning point, this is a turning point. Okay, they're not metaphorical turning points, they're actual turning points, right? It turns out, if you figure out the number of zeros a function has, it will always have that number minus 1 turning points. Okay, so if a function has n zeros, it will have n minus 1 turning points. And how do we figure that out? By this. Look at this function here. The leading term is 3x to the 6. The degree here is 6, which means it is allowed to have up to 6 zeros, which means it is allowed to have up to 5 turning points. Okay? All right, questions? Okay, so take a look here. State the number of possible real zeros. Okay, so the degree is 3. So possible zeros, 3. Possible turning points, 3 minus 1, 2. And then we want to determine all of the real zeros, right? So to determine the real zeros, what we're going to do is set this function to 0. And now we factor algebra 2 style. So first take out an x. And now factor x plus 4, x plus 1. So my zeros are 0, -4, -1. Okay.
Do we need to write them separately, or can we just write x equals 1 and separate with commas?
You can do commas, yes. All right, let me do these two and then we'll stop for today. So this one, look, it's x to the 4, blah, blah, blah. And look at what I wrote here as a hint. I said that this is factoring in quadratic form, right? So look at what we have. The first term has some exponent, 4. The next term, the exponent is half of that. And then there is a constant. You never think about quadratics that way, but that's pretty much the form of it. You know, if you have something like this, you have an exponent. The next exponent is half of that, then you have a constant. So anytime you have that pattern, you can factor it like a quadratic equation. So if it's x to the 8 minus 8x to the 4 plus 15, you could do the same. Okay? So this, we're going to factor it like a quadratic equation, but instead of x and x, I put in x squared and x squared. Did you guys do these last year? A little, yeah. Okay, so now 15 and -8, it's going to be -5 and -3. Sorry. Set it equal to 0. So now we can say x squared minus 5 equals 0. X squared minus 3 equals 0. Oh, I forgot to do the predictions for this, right? We can do that later. So x squared equals 5. X is plus or minus √5. X squared equals 3, and I take a square root. X is plus or minus √3. So those are the zeros. But what could we have predicted? Since the degree is 4, we could have said possible zeros were 4 and turning points 3. What about here? Possible zeros, 4. Turning points, 3. Okay, let's factor this guy. Quadratic form again. X squared, right? How do we factor this? Does that work? Yeah. And same thing, x squared minus 3 equal to 0. X squared minus 1 equal to 0. Add 3 to both sides. X equals plus or minus root 3. And here, x squared equals 1. Take a square root. X is plus or minus 1. All right? Okay. And that's where I will stop for today, and I will take some questions.